Welcome to a new deep dive. Today, we're shifting gears a bit on prompt engineering.
Yeah. How so?
Well, we're not just looking at what makes a good prompt, we're like putting on our engineering hats.
Ah, okay. Looking under the hood.
Exactly, how it all actually works. You shared some great info. And our mission today is really to unpack the nuts and bolts.
Right. Why getting prompts right isn't just, getting the answer you want.
It's also about efficiency, isn't it? How, well-optimized prompts can actually make the LLM perform better.
Totally. And maybe even save on tokens, which has real practical consequences.
It's definitely more than just chatting politely with an AI.
Oh, for sure. There's a proper engineering side to it. And being thoughtful about prompts, that can directly mean, using the LLM more efficiently.
Cutting down processing time, maybe costs.
Exactly.
Yeah.
Streamlining the whole thing.
And I guess to engineer those good prompts, we kind of need to peek behind the curtain.
Yeah, you need to understand how the LLM actually digests the text we give it.
Like knowing how your car engine works helps you drive better, something like that.
That's a great analogy. And building on that, we should definitely look at those key settings engineers use.
You mean like temperature, top K, top P?
Precisely.
Yeah.
They're not just like abstract concepts, they're actual controls.
Practical levers you can pull to tweak how random or predictable the output is.
Yeah. Understanding those is key to fine-tuning.
Okay, let's dig into that. Maybe start with output length. I mean, you'd think limiting tokens forces conciseness, right?
You would think so, wouldn't you? But what the info shows is that a token limit, it's really just a hard stop.
A hard stop.
Yeah, it just tells the model, okay, stop generating now.
Yeah.
It doesn't mean it was like aiming for brevity before that point.
Ah, so it could just get cut off mid-sentence or mid-thought.
Exactly, which can be, well, pretty important for some techniques like React. The model might do extra thinking after it technically found the answer.
So limiting tokens doesn't make it think faster or shorter, just stops it sooner.
Right. It's less about saying be brief and more like setting a maximum budget.
And generating more tokens, well, that has real consequences, I imagine.
Absolutely. Every extra token means more compute power,
Which means,
more energy used, potentially slower response times, and yeah, sometimes higher cost depending on the service.
so from that engineering angle, getting what you need with fewer tokens is a big deal.
A very significant factor, yes. Optimization matters.
Got it. Okay, so how do these models decide the next word? It's not random guessing, is it? You mentioned probabilities.
Right. That's really the heart of it. An LLM doesn't just pick one best next word.
Yeah.
No, it calculates a probability for every single possible word in its vocabulary being the next one.
Wow. Okay, so it's like this huge list of options with scores.
Exactly. Constantly updated. And those controls we mentioned, temperature, top K, top P, they're the ways the model uses those probabilities to actually pick the next token.
Okay, let's tackle temperature first. Sounds slightly vague, like the AI's mood.
You could sort of think of it that way, I guess. Temperature controls the randomness.
Randomness, okay.
So a low temperature, especially 0, which is called greedy decoding, makes the output very predictable, very focused.
Meaning it just picks the highest probability word every time?
Almost always, yeah. But interestingly, even at 0, if two words have the exact same top probability, well, how it breaks that tie can cause tiny variations.
Okay, so low temp equals predictable, straight answers. What about cranking it up, turning up the heat?
Well, when you increment the temperature, you're basically telling the model, hey, consider some of those less probable words too.
Okay.
It adds more randomness. The output gets more diverse, maybe more creative, sometimes unexpected.
But I guess there's a risk there.
Oh, definitely. Crank it way too high, and it might start picking really unlikely words. Things get nonsensical pretty fast.
So it's a balance. Predictability versus exploration.
That's a perfect way to put it. Precision versus brainstorming.
Makes sense. Now, what about top K and top P? They sound like filters?
They are, essentially. Both are ways to narrow down the choices based on those probabilities we talked about, focusing the model.
Let's do top K first. What's the K?
K is just a number. Simple as that. If you set K to, say, 40,
Okay.
the model only looks at the 40 words with the highest probability scores for the next step.
So a higher K means more options considered, more variety.
Exactly. And a really low K, like K1, well, that's basically greedy decoding again. Always the top choice.
Right, the single most likely. Okay, K is the size of the candidate list. What about top P nucleus sampling? Sounds a bit more complex.
It's a slightly different way to slice it. Instead of a fixed number, top P looks at the cumulative probability.
Cumulative. How?
It selects the smallest group of top words whose probabilities, when added together, exceed a certain threshold. That's the P.
Ah, so P is a probability target, like 0.9 or something.
Exactly. P goes from 0 to 1. A P near 0 is greedy again. A P of 1 means theoretically consider everything.
So top P is about probability weight, not just rank. How do you choose, K or P or both?
That's the million-dollar question sometimes. The best advice seems to be experiment.
Come out.
Yeah. Play with different values for K, different values for P. See what works best for your specific task and the model you're using. Sometimes using them together is the sweet spot.
Okay, and how do all three interact? Temperature, top K, top P. Sounds like they could clash.
They interact in a specific order, usually, if you set all three.
Yeah.
The model generally filters first. It finds the words that satisfy both the top K condition, being in the top K, and the top P condition being in the smallest set, exceeding P.
Okay, so it finds the overlap between those two lists.
Pretty much. That becomes the final pool of candidates. Then, the temperature setting gets applied to that pool.
To add the randomness element during the final selection from that filtered list?
You got it. Filter first, then apply temperature's randomness.
What if, say, temperature isn't an option on a platform, or only K is?
Good question. If only top K or top P is available, it just uses that one filter. If temperature isn't available, but K and or P are, it usually just picks randomly from the tokens that made it through the KP filtering.
Okay. Can one setting just completely override the others if you set it to an extreme?
Oh, absolutely.
Yeah.
Extremes dominate. Set temperature to 0.
Greedy decoding.
Right. It makes top K and top P irrelevant because it's always picking the top probability token anyway.
And top K1.
Same thing. Forces the top choice, ignores temperature and top P.
Can top P near 0?
Yep. Usually forces the top choice too,
Yeah.
making the others moot. On the flip side, a really high top P, like a 1 or a massive top K, basically includes almost everything, so the filtering doesn't do much.
So these are definitely powerful knobs to turn, but you need to be careful how you turn them.
You really do.
The info you share also gave some starting points, didn't it, depending on the goal?
It did, yeah. Some useful rules of thumb. For a decent balanced coherence, but with a bit of, flexibility.
Yeah.
Maybe start around temperature 0.2, top E 0.95, and top K 30.
Okay, balanced start. What about more creative stuff?
For more creative output, you could push things. Maybe try temp 0.9, top E 0.99, and top K 40. More room for exploration.
And for less creative, more factual tasks.
Then dial it back. Perhaps temp 0.1, top E 0.9, top K 20. More constrained.
And what about things with one right answer, like math?
For that, the recommendation is usually start with temperature at 0. Try for maximum predictability first.
Those are really handy starting points. But there was also a warning, right? About giving too much freedom.
Yes, absolutely. If you push the randomness too high with like super high temp or K or P values,
The output gets messy.
it can become less focused, less relevant to what you actually asked for. It's always that trade-off, exploration versus staying on task.
Right. And we should also mention the repetition loop bug. That sounds frustrating.
It really can be. That's when the model just gets stuck, repeating the same word or phrase over and over.
What causes that? Too much randomness? Or too little?
Interestingly, it can be either. Settings that are too rigid, too deterministic, or too loose and random can sometimes trigger it, or just weird combinations of top K and top P.
So finding that sweet spot through experimentation is key again.
It really is. That's often how you get that high-quality coherent output without the weird loops.
So wow, it's clear that engineering prompts isn't just finding the magic words, it's also deeply about understanding these controls.
Yeah, the tuning. How to adjust the engine, not just steer the car.
Optimal performance, efficiency, avoiding weird behavior. It's all connected. This has been really illuminating on the tech side.
Definitely. When you understand these mechanisms, temp, KP, token limits,
Yeah.
you can be much more strategic with LLMs.
It moves prompt engineering from maybe an art towards more of an engineering discipline.
I think that's a fair way to put it.
So as you can probably tell by now, looking at prompt engineering from this engineering angle shows it's not only what you say, but crucially how the LLM processes it.
And how you can tweak those settings, those under-the-hood controls.
Right. For efficiency, getting the creativity level you want, or maybe getting more predictable results. We've touched on optimizing tokens, how the prediction actually happens with probabilities.
And the big three. Temperature, top K, and top P, and how they all work together.
Hopefully this deep dive has given you a a much clearer picture of the engineering side of things when you're working with these incredibly powerful AI models.
Yeah, understanding the principles really helps you get the most out of them.
Thanks for diving in with us today. If you found exploring these AI engineering insights useful, definitely subscribe for more deep dives into this fascinating world of artificial intelligence.